There's a clock ticking beneath Hawaii, and it's not keeping Earth time. January 12th, 2026. Kīlauea volcano erupts with 10,000 megawatts of thermal power, crossing into extreme anomaly territory. But 48 hours earlier, something rewired the system. Dual coronal holes on the sun aligned perfectly, launching plasma streams toward Earth just as the volcano was ready to blow. Then, a 4.4 magnitude earthquake. One event is geology. 5 events in 72 hours is synchronization. Stay until the end, because if volcanoes are listening to the sun, then every eruption we've ever called random might actually be an answer to a question we didn't know was being asked. Subscribe and follow along as more data from Kīlauea and the sun continues streaming in. Because what unfolds over the coming weeks will either confirm that these are random coincidences or reveal dangerous blind spots in how we understand Earth's response to space weather. This isn't about predicting the next eruption. It's about recognizing the pattern that's already here. On December 1st, 2025, satellite systems monitoring Kīlauea volcano registered something they haven't seen in months. The Mirova thermal detection system, which watches infrared signatures from orbit, flagged what's called an extreme thermal anomaly. That's a technical classification, and it means the radiative power output exceeded 10,000 megawatts. To put that in perspective, that's enough energy to power a small city being released continuously from a single volcanic vent. But here's the thing that should make you pause. The heat itself isn't the story. Everyone expects Kīlauea to be hot. It's been erupting on and off for over a year now. What matters is when this happened, and why episode 40 stands out from everything that came before it. Episodes 38 and 39 never reached this threshold. They were active, sure. Lava fountains, surface flows, all the visual drama you'd expect. But neither one crossed into extreme territory according to the monitoring systems. That makes episode 40 a return to a higher energy state, not a continuation of what was already happening. The volcano didn't just keep going, it escalated. And escalation always demands an explanation, especially when the timing lines up with other events in ways that make geophysicists uncomfortable. Let me show you what I mean by timing. Between November 30th and December 2nd, 3 separate phenomena converged. A G2 geomagnetic storm peaked in Earth's magnetosphere. High-speed solar wind from a pair of coronal holes on the sun arrived at our planet. And sustained lava discharge began at Kīlauea's Halema Umau crater. None of these events are rare by themselves. Geomagnetic storms happen dozens of times a year. Coronal holes rotate into view every month or so. Kīlauea erupts more than almost any other volcano on Earth. But when you stack them on top of each other within a 72-hour window, you start to notice something that conventional models don't handle well. Correlation without obvious causation. Pattern without accepted mechanism. Now, before we go any further, let me be clear about what this video is and what it isn't. This is not a beginner's guide to volcanology. I'm not going to explain what magma is or why Hawaii exists. If you're here, you probably already know the basics, or you're willing to learn as we go. This is also not a video claiming the sun directly causes volcanic eruptions in some simplistic mechanical way. That's not how planetary systems work. What we're exploring is something more subtle and more unsettling. The possibility that Earth operates as a responsive system, not a closed one. That external inputs, even subtle ones, can alter the timing and intensity of geological events when internal conditions are already primed, and that we might be watching this happen in real time without fully understanding what we're seeing. Kīlauea matters for this investigation in ways that other volcanoes don't. It's the most heavily instrumented volcano on the planet. Seismometers, tilt meters, gas sensors, GPS arrays, thermal cameras. Everything that can be measured is being measured, continuously, and has been for decades. The data resolution is extraordinary. You can watch magma move through the plumbing system in near real time, You can see pressure changes, gas emissions, ground deformation, all updating faster than almost anywhere else in the world. That makes Kīlauea function like a sensor array for processes we don't fully understand yet. It's not just erupting, it's broadcasting information about what's happening beneath our feet, and possibly responding to influences from beyond our atmosphere. The magma response times at Kīlauea are fast, unusually fast. Changes in deep magma supply can manifest at the surface within days or even hours, not weeks or months, like at other volcanic systems. That speed matters when you're trying to correlate surface activity with external triggers. If there's a lag of several weeks between a solar event and a volcanic response, the connection gets muddied by everything else that happens in between. But when the response window is tight, the signal becomes clearer. You can start to separate noise from pattern. You can start to ask uncomfortable questions about whether what we call coincidence might actually be synchronization. So when I tell you that episode 40 hit an extreme thermal threshold within 48 hours of a geomagnetic storm peak, and that this happened during one of the most magnetically active periods in recent months, you should understand that this is the kind of timing that makes researchers stop and look twice. Not because it proves anything, but because it fits a pattern that's been quietly building for years, showing up in data sets that most people never look at, and that mainstream volcanology has largely chosen to ignore because there's no accepted framework for explaining it. At what point does repeated correlation stop being coincidence and start being system behavior? That's the question we're circling around, and it's not a comfortable question because the answer has implications for how we understand planetary dynamics, space weather risk, and what it means to monitor geological hazards in an era where we're finally seeing connections we couldn't detect before. If Earth's internal systems are more externally sensitive than we've assumed, then our models are incomplete. Not wrong necessarily, just missing variables. And missing variables in safety-critical systems is how disasters happen. But if timing is the real issue here, then November 26th is where the clock broke. Because 10 minutes after episode 37 ended, something happened that shouldn't have been possible. And it changed everything that came after. 10 minutes. That's how long passed between the end of episode 37 and a magnitude 4.4 earthquake that struck inside Volcanoes National Park on November 26th, 2025. 10 minutes is nothing in geological terms. It's barely enough time for magma to move a few meters through a conduit. It's not enough time for regional stress to redistribute. It's not enough time for anything significant to happen through normal tectonic processes. And yet, there it was. An earthquake substantial enough to be felt across the island, occurring almost immediately after an eruption stopped, in a location that raised questions about what was actually happening beneath Kīlauea's edifice. The timing alone is weird. Earthquakes at active volcanoes are common, obviously. Magma movement generates seismic signals constantly. But the pattern matters. Earthquakes usually precede eruptions as magma forces its way upward, fracturing rock and opening pathways. They also happen during eruptions as pressure adjusts and lava drains from reservoirs. What's less common is a significant earthquake arriving the moment an eruption stops, as if something that was holding pressure suddenly released. That's the kind of timing that suggests a state change in the plumbing system itself. Let me walk you through what a magnitude 4.4 can do to a volcanic system. It's not large enough to cause catastrophic collapse or trigger massive landslides, but it's absolutely large enough to reopen sealed fractures, alter permeability in the shallow crust, and redistribute pressure across existing magma pathways. Think of it like this. The volcanic system is a network of conduits, some active, some dormant, all filled or partially filled with molten rock at different depths. When an earthquake hits, it doesn't just shake the surface. It propagates stress waves through the entire network. Sealed cracks can pop open. partially molten zones can become more fluid. Pressure that was bottled up in one location can suddenly find a new route to the surface. The system doesn't break, it reorganizes. And that reorganization shows up in the data immediately. After November 26th, the behavior of Kīlauea's summit changed. Inflation and deflation cycles, which had been relatively gradual and predictable, became sharper and more pronounced. The volcano was breathing differently. Discharge phases during subsequent eruptions shortened but intensified. Episodes lasted fewer days, but produced higher thermal outputs and more vigorous lava fountaining. The system wasn't becoming unstable in the sense of imminent catastrophe, but it was becoming more responsive, more sensitive to small inputs, like a guitar string tuned tighter, where less energy is required to produce a louder note. This is where the concept of a sensitized system becomes important. Volcanologists talk about this in terms of stress thresholds and failure envelopes, but the core idea is simple. A volcano that's been mechanically altered by an earthquake doesn't need as much additional forcing to respond. If you've just reorganized the plumbing, even minor changes in magma supply or external pressure fluctuations can trigger disproportionate surface effects. The earthquake didn't cause future eruptions. It changed the gain on the system. It turned up the sensitivity. And that means everything that happened afterward, including episode 40, has to be understood as downstream behavior, not a new phenomenon starting from scratch. Now, let me be extremely clear about what I'm not saying. I'm not claiming the November 26th earthquake was triggered by solar activity. I'm not saying it was caused by tidal stress or planetary alignment or anything else external. Earthquakes at volcanic systems have internal drivers: magma movement, pressure changes, structural weaknesses in the crust. All of that is still true. What I am suggesting is that the earthquake altered the baseline state of the system, and that the altered state may be more susceptible to external timing influences than the pre-quake state was. It's a question of sensitivity, not causation, and sensitivity is what makes timing correlations meaningful instead of random. Think about what this means for episode 40. You have a system that's been mechanically primed by a significant earthquake. You have magma supply rates that are already elevated from ongoing activity. And then you have a geomagnetic storm and high-speed solar wind arrival occurring right when the volcano is in an inflation phase, building pressure for the next discharge event. If the system is sensitized, then even a small external push, something that wouldn't matter under normal conditions, could be enough to tip the balance, not creating the eruption, but advancing the timing, changing the intensity, altering the character of the event in ways that make it cross thresholds it wouldn't have otherwise reached. This is the part where mainstream volcanology gets uncomfortable. Because if you accept that external factors can modulate the timing of eruptions in a sensitized system, even if they're not providing the energy for the eruption itself, then you have to start monitoring those external factors. You have to include space weather in hazard assessments. You have to look at solar wind data alongside seismic data. And that requires crossing disciplinary boundaries that have been rigidly maintained for decades. Volcanologists study volcanoes. Space physicists study the magnetosphere, and rarely do the two communities talk to each other in meaningful ways. But Kīlauea is forcing that conversation, whether anyone wants it or not. So if the system changed internally, and we can see evidence of that change in the post-quake data, the next question is obvious. What's been tapping it externally? What's providing the timing signal that seems to correlate so consistently with eruptive activity? To answer that, we have to leave Earth for a moment. We have to look 93 million miles away. We have to talk about the sun, and we have to talk about the one form of solar output that almost everyone ignores. The sun doesn't just shine, it exhales, constantly. A stream of charged particles, mostly protons and electrons, flows outward from the solar corona at speeds ranging from 300 to over 1,000 kilometers per second. This is the solar wind, and it's been bathing Earth in a continuous plasma flow for billions of years. Most people have heard of solar flares. Some have heard of coronal mass ejections. Almost nobody talks about the solar wind unless they're studying the magnetosphere or satellite drag. But if you're trying to understand external timing influences on Earth's geological systems, the solar wind is where you should be looking. Not because it's dramatic, because it's persistent. Let me clarify some terminology because this matters. Solar flares are bursts of electromagnetic radiation. Photons traveling at the speed of light, reaching Earth in about 8 minutes. They can disrupt radio communications and create auroras, but they don't last long. Coronal mass ejections are eruptions of plasma and magnetic field ejected from the sun's atmosphere. They're slower than flares, taking 1 to 3 days to reach Earth, and they can cause significant geomagnetic storms when they arrive. But they're also relatively rare, maybe a few dozen big ones per year during solar maximum. The solar wind, on the other hand, is always there. It doesn't stop. And when it's coming from certain regions on the sun, it doesn't just flow, it accelerates. Coronal holes are regions where the sun's magnetic field opens up and allows plasma to escape more easily. They appear as dark patches in ultraviolet images of the solar corona. And when they're facing Earth, they launch high-speed streams of solar wind that can persist for days or even weeks as the sun rotates. These streams are different from CME impacts. They're not sudden shocks. They're sustained increases in particle flux and velocity, often reaching 700 kilometers per second or more. And when a fast stream catches up to a slow stream ahead of it, you get something called a co-rotating interaction region, or CIR. That's where the density and magnetic field strength compress, creating conditions that can drive geomagnetic activity for extended periods. CIRs are understudied compared to CMEs. There's less funding, less attention, fewer papers, but they're incredibly important for understanding long-duration energy input into Earth's magnetosphere. A CME hits, and then it's over within hours. A CIR can persist for multiple days, maintaining elevated geomagnetic conditions the entire time. If you're looking for a mechanism that could provide a sustained timing signal rather than a one-time trigger, CIRs are much better candidates than flares or CMEs. And guess what was happening in late November and early December 2025? Dual coronal holes, rotating into Earth-facing positions, launching overlapping high-speed streams that created a sustained period of elevated solar wind velocity and geomagnetic activity. The geometry of these dual streams matters more than most people realize. When a single coronal hole faces Earth, you get a relatively clean high-speed stream that arrives, causes some geomagnetic disturbance, and then passes as the sun rotates. The magnetosphere responds, recovers, and returns to baseline. But when two coronal holes are positioned such that their streams overlap or arrive in rapid succession, the recovery time disappears. The magnetosphere gets compressed by the first stream, starts to relax, and then gets hit again before it can fully stabilize. This creates a ratcheting effect where the cumulative stress builds higher than either stream would produce alone. The magnetic field lines get stretched and twisted. Plasma density in the magnetosphere increases, and the electric currents that flow between the magnetosphere and the ground intensify and persist longer than they would from a single isolated event. Now we get to the observations that make people nervous. Kīlauea has erupted during or shortly after geomagnetic storms more times than chance would predict. I'm not going to cite specific papers here because this is a video, not a journal article, but the correlation has been documented by multiple research groups using different methodologies. The same pattern shows up at other volcanic systems too, though less clearly because most volcanoes don't have Kīlauea's instrumentation or eruption frequency. The effect isn't strong. It's not like you can predict eruptions from space weather alone, but it's there, subtle, persistent, and completely unexplained by conventional models. The statistical significance of these correlations is worth dwelling on for a moment. When researchers analyze decades of eruption data alongside space weather indices, they find that eruptions cluster around periods of elevated geomagnetic activity at rates that exceed what random chance would produce. The probability values are often borderline, hovering around the 5% threshold that scientists use to distinguish signal from noise. But borderline doesn't mean absent. It means the effect is real, but weak, or the sample size is still too small, or there are confounding variables we haven't controlled for properly. Any of those interpretations suggests more research is needed, not dismissal of the entire line of inquiry. What makes the Kīlauea correlations particularly compelling is the consistency. This isn't a one-time coincidence. It's a pattern that repeats across multiple eruption cycles, multiple solar cycles, and multiple measurement systems. Different researchers using different statistical methods arrive at similar conclusions. The timing relationship shows up whether you're looking at eruption start times, peak thermal output, or changes in eruption style. That kind of consistency across multiple independent analyses is exactly what you want to see when evaluating whether a correlation might represent genuine physical coupling rather than spurious pattern matching. So what's the mechanism? How does solar wind, which interacts with Earth's magnetosphere hundreds of kilometers above the surface, influence magma movement in the crust? The short answer is, we don't know for certain. The longer answer involves telluric currents and magnetospheric compression and possible coupling between electromagnetic fields and partially conductive magma. But all of that is speculative at this point. What we can say is that when the magnetosphere compresses during geomagnetic storms, electric currents flow through the ground. These are called telluric currents, and they're measurable. Power grids detect them. Pipelines detect them. And if currents are flowing through the crust, they're flowing through volcanic systems too. Whether those currents can influence magma dynamics is an open question, but the timing correlations suggest something is happening. Telluric currents aren't some exotic phenomenon that only appears during extreme space weather. They're flowing constantly, varying in intensity based on magnetospheric activity. During quiet times, the currents are weak and diffuse. During storms, they intensify and concentrate along paths of least resistance in the crust. Geological structures like fault zones, fracture networks, and regions with high fluid content are more conductive than solid crystalline rock. Volcanic systems, with their networks of magma-filled conduits and hydrothermally altered rock, are particularly conductive. So when telluric currents strengthen during geomagnetic storms, volcanic systems experience disproportionately large current flow compared to surrounding terrain. What that current flow does to magma behavior is still being worked out, but possibilities include altering gas bubble nucleation rates, changing the viscosity of partially molten rock through electromagnetic heating, or even influencing crystallization processes that affect magma ascent dynamics. Let me stress this as clearly as possible. Trigger does not mean cause. The sun is not providing the energy for volcanic eruptions. Magma chambers are heated by radioactive decay and residual planetary formation energy in the mantle. That's where the thermal energy comes from. What the solar wind might be doing is providing a timing signal, a small perturbation that nudges a system that's already close to erupting. Think of it like this. You have a boulder perched on top of a hill. The gravitational potential energy is already there. The hill is already steep. The boulder is already unstable. All it needs is a small push. The push doesn't create the energy that sends it rolling down. It just determines when that energy gets released. The sun doesn't light the fuse. It flicks the table. This distinction is absolutely critical because failure to maintain it is why these ideas get dismissed so easily. Nobody credible is claiming that solar activity generates volcanic eruptions from nothing. The energy budget doesn't work. A typical volcanic eruption releases energy equivalent to a large nuclear weapon. Solar wind interactions with the magnetosphere even during major storms, transfer orders of magnitude less energy into the solid Earth. There's no direct energy pathway that could cause an eruption. But causing an eruption and timing an eruption are completely different processes with completely different energy requirements. Timing only requires enough perturbation to tip a system that's already critical, and critical systems, by definition, are sensitive to small inputs. That's what makes them critical. Mainstream geophysics is deeply skeptical of this idea, and for understandable reasons. There's no accepted physical mechanism. The energy budgets don't obviously match. And there's a long history of fringe theories claiming cosmic influences on everything from earthquakes to stock markets, most of which have been thoroughly debunked. So any suggestion that external factors modulate volcanic activity gets lumped in with that noise and dismissed. But dismissal without investigation is just as unscientific as belief without evidence. And the timing correlations at Kīlauea are strong enough that they warrant serious attention, not reflexive rejection. The history of science is full of examples where subtle effects were dismissed as impossible until better instrumentation revealed they were real. Continental drift was ridiculed until seafloor spreading was discovered. Meteorites were considered superstition until someone actually analyzed one chemically. The connection between electromagnetic fields and biological systems was mocked until magnetotactic bacteria were found. None of these discoveries violated fundamental physics. They just revealed coupling mechanisms that existing paradigms hadn't anticipated. The question isn't whether solar wind can affect volcanoes in principle. The question is whether the specific mechanism, whatever it turns out to be, operates strongly enough to produce observable timing effects. And the only way to answer that is through systematic investigation, not a priori dismissal. What makes episode 40 different from previous eruptions is that it didn't happen in isolation. It didn't occur during a random moment in the solar cycle or during quiet geomagnetic conditions. It happened inside a convergence window. And convergence is what we need to talk about next. Because when multiple external factors align simultaneously with internal volcanic conditions, the probability of correlation by chance drops significantly. And the question shifts from whether there's a pattern to what that pattern actually means. We're about to enter territory where the number of coinciding variables becomes impossible to ignore, even for the most conservative skeptic. And that's where this story stops being about volcanology and starts being about something much larger. There are moments in time when multiple systems align in ways that make forecasters uncomfortable. Not because anything catastrophic is guaranteed to happen, but because the uncertainty bands widen. Predictability decreases. The number of variables interacting simultaneously exceeds what models can handle cleanly. Late November through early December 2025 was one of those moments. And if you were watching the right data streams, the convergence was impossible to miss. Let me lay this out chronologically so you can see how tight the window actually was. On November 30th, two separate high-speed solar wind streams from dual coronal holes began impacting Earth's magnetosphere. One stream was already elevated from a coronal hole that had been facing Earth for several days. The second stream arrived as a different coronal hole rotated into position, creating an overlap. This isn't a coronal mass ejection scenario. CMEs are discrete events. This was sustained, elevated particle flux from persistent source regions. The solar wind velocity exceeded 600 kilometers per second for multiple consecutive days. Geomagnetic activity jumped to G2 storm levels, with the KP index hitting 6 and staying elevated through December 2nd. At the same time, Earth was approaching a new moon phase. New moon occurred on December 1st. Tidal forces from the moon's gravity are always present, but they peak during new moon and full moon when the sun, Earth, and moon align. Now, lunar tidal effects on volcanic systems are weak, extremely weak. We're talking about stress changes measured in kilopascals, which is orders of magnitude less than the internal pressure in a magma chamber. Under normal circumstances, Tidal stress is irrelevant to eruption timing, but these weren't normal circumstances. Kīlauea had just been mechanically reorganized by the November 26th earthquake. It was in an active discharge cycle, and it was already inflating toward another eruption. In a sensitized system, even tiny stress changes can matter if they occur at exactly the right moment in the pressure buildup cycle. So you have elevated solar wind, you have geomagnetic storm conditions, you have peak lunar tidal stress, and you have an active volcano that's primed and ready to erupt, all of this converging in a 72-hour window. Episode 40 began on December 1st. The Extreme Thermal Anomaly was detected on December 1st. The timing isn't subtle, it's blatant. And yet, if you go looking for official statements from USGS or Hawaiian Volcano Observatory acknowledging any connection to external factors, you won't find them. Because acknowledging the correlation requires explaining it, and there's no accepted explanation. So the safer institutional response is to treat each eruption as an independent internal event and ignore the external context entirely. Dual coronal holes are different from single high-speed streams in important ways. When you have two streams overlapping, the interaction region between them becomes more complex. Magnetic field orientations fluctuate more rapidly. Density gradients steepen. The coupling efficiency between the solar wind and the magnetosphere can actually increase because the magnetosphere doesn't have time to relax between impacts. It's like being hit by waves in the ocean. One wave you can handle, but when waves come in rapid succession without gaps, the cumulative effect is much harder to recover from. The magnetosphere was getting hammered for days, not hours, and that sustained compression creates sustained telluric current flow in the ground, sustained electromagnetic perturbations in the crust, sustained timing signals that a sensitive volcanic system might respond to. Now let's talk about something that makes volcanologists uncomfortable. Tidal triggering is real. It's been documented. But it only works under very specific conditions. The system has to already be at, or very near, failure threshold. The tidal stress has to occur at the right phase of the internal pressure cycle. And even then, the effect is to advance eruption timing by hours or maybe days, not create eruptions that wouldn't have happened anyway. But here's the thing. If tidal stress can advance timing, why can't other external perturbations? Why is it okay to acknowledge that the moon's gravity can modulate volcanic activity, but not okay to investigate whether solar wind or geomagnetic storms can do the same thing? The physical principle is identical. Small external stress applied to a critical system. The only difference is the mechanism. And mechanism is something you figure out through research, not dismiss through assumption. There's another possibility that nobody likes to discuss, and it's the idea that lack of escalation doesn't necessarily mean lack of effect. What if the external forcing during the convergence window caused internal pressure redistribution rather than immediate release? What if energy that would normally have been released through smaller, more frequent events got buffered and stored for a larger event later? Volcanic systems don't have to respond instantly to perturbations. They can absorb stress, redistribute it through the plumbing network, and release it when internal conditions finally allow. That means the real impact of the convergence window might not have been episode 40 at all. It might be whatever comes next, and we won't know until it happens. This is where we start asking uncomfortable questions. Are we mistaking delayed response for stability? Are we interpreting lack of immediate catastrophe as evidence that external factors don't matter, when in reality, the response time is just longer than our attention span? Geophysical systems operate on timescales that don't match human observation windows. Something that looks stable over weeks or months might be building toward release over years. And if external timing signals can modulate that build-up process, even subtly, then our hazard models are missing something critical. But the convergence window in late November and early December wasn't just about solar wind and tides. There are other variables in play. variables that mainstream science barely acknowledges because they don't fit existing models and because the data is incomplete. Variables like planetary positions. Variables like objects from outside our solar system drifting through the inner asteroid belt. And this is where speculation begins. But it's speculation worth taking seriously, because the alternative is pretending we understand systems that we demonstrably don't. Let me be extremely clear about what you're about to hear. This section is speculative. It's investigatory. It's not established science. There are no peer-reviewed papers definitively proving the mechanisms I'm about to discuss. But there are observations, and those observations don't fit the models we currently use. So we're going to talk about them honestly, without pretending we have answers we don't have, and without dismissing possibilities, just because they're unfamiliar. Planetary alignments come up constantly in alternative geophysics discussions, usually in ways that make actual scientists roll their eyes. The idea that planets lining up can cause earthquakes or volcanic eruptions has been repeatedly debunked because the gravitational forces involved are minuscule at terrestrial distances. Venus, Mars, Mercury, Jupiter, they're all pulling on Earth constantly, but the tidal stress they create is negligible compared to what the Moon produces. So most researchers dismiss planetary alignment theories entirely and move on. But dismissal assumes we understand all the relevant mechanisms, and that's a bold assumption when we're still discovering basic facts about how the solar system works. Gravitational effects aren't the only way planets can influence each other. Magnetic fields matter. Plasma interactions matter. The solar wind doesn't flow uniformly through the solar system. It gets deflected and channeled by planetary magnetic fields. It creates wake regions and bow shocks. When multiple planets are on the same side of the sun, the configuration of the interplanetary magnetic field changes. Current sheets tilt differently. Co-rotating interaction regions form in different locations. None of this is controversial. It's basic heliophysics. What's controversial is suggesting that those changes could influence Earth's magnetosphere in ways that cascade down to geological effects. But if you've already accepted that geomagnetic storms can modulate volcanic timing, then you've already accepted that magnetospheric conditions matter, and magnetospheric conditions depend on the broader interplanetary environment, which means planetary positions aren't irrelevant. They're just subtle. Venus was in inferior conjunction in late November 2025. That means it was between Earth and the Sun, at its closest approach to our planet. Mars was visible in the evening sky, approaching opposition. Mercury was in the morning sky after a recent elongation. None of this caused anything, but all of it contributed to the magnetic and plasma environment that Earth was experiencing during the Convergence window. Were these positions necessary for episode 40 to occur? Almost certainly not. Did they add additional variables to an already complex system state? Quite possibly. And in systems operating near critical thresholds, additional variables matter even when they're small. Now we get to 3I/Atlas, and this is where even the speculation becomes uncertain because the object itself is not fully characterized. 3I/Atlas is a reported interstellar object discovered in 2024 that's currently somewhere in the inner solar system. I say reported because its interstellar origin hasn't been definitively confirmed by all observational teams. What we know is that it has an unusual trajectory that doesn't match typical asteroid or comet orbits. What we don't know is basically everything else: its composition, its magnetic properties, its exact position at any given time. It's a source of intense interest among astronomers, and a source of wild speculation among people trying to explain anomalies in other fields. Why do interstellar objects matter for this discussion? Because they come from outside our solar system. They formed in different stellar environments with different magnetic histories. They've been traveling through interstellar space, potentially carrying magnetic field structures that don't match solar system norms. When an object like that enters the inner solar system, It could theoretically perturb the interplanetary magnetic field in ways that solar system natives don't. Could it influence Earth's magnetosphere from millions of kilometers away? Probably not directly. Could it create wake effects or magnetic anomalies that modify how solar wind streams interact with Earth? Maybe. Do we have enough data to know for sure? Absolutely not. The reason institutions dismiss potential links between interstellar objects and geological activity is simple. There's no mechanism. There's no precedent. And the scientific method demands that extraordinary claims require extraordinary evidence. Fair enough. But the scientific method also demands that we investigate anomalies when they appear, not ignore them because they don't fit existing frameworks. And there are timing anomalies in the geophysical data from late 2025 that haven't been adequately explained. Maybe they're just noise. Maybe they're unrelated events that happen to cluster randomly. Or maybe they're signals that we don't know how to interpret yet because we're missing key pieces of the puzzle. Conservative modeling culture in geophysics exists for good reasons. People's lives depend on hazard forecasts. You can't afford to chase every speculative idea when you're trying to protect communities from real dangers. But conservative culture can also become dogmatic. It can create blind spots. It can cause researchers to stop looking at data that doesn't match expectations. And when you stop looking, you stop learning. The institutions that monitor volcanoes do extraordinary work with limited resources and high stakes. But they're also bound by paradigms that haven't fully caught up with what observational technology is showing us. We can detect correlations now that were invisible 20 years ago. We can track timing relationships across different physical systems with unprecedented precision. And those correlations are telling us that Earth is more connected to its space environment than traditional models account for. So here's where we draw the line. Hypothesis is not the same as narrative framing. Narrative framing is not the same as evidence. 3I/Atlas, being in the inner solar system during a period of increased volcanic activity, is interesting. It's worth noting. But it's not proof of causation. It's not even proof of correlation unless we have much better data on the object's position and properties than we currently do. What it is a reminder that the solar system is a complex, dynamic environment with more variables than we typically consider when we're modeling Earth's behavior. And maybe that's the real takeaway from all of this. Not that we've discovered a hidden trigger for volcanic eruptions, but that we've discovered how much we still don't understand about how Earth interacts with the space around it. The second takeaway is that Earth may behave more like a coupled system than a sealed one. More like an instrument responding to multiple inputs than an isolated object operating purely on internal energy. Kīlauea might be the best sensor we have for detecting those coupling effects because it responds quickly and we measure it obsessively. But if Kīlauea is responding to external timing signals, then other systems probably are too. We just haven't been looking at them the right way. And that raises a final question. Is Kīlauea the only place showing these patterns? Or are there other red flags appearing in other data sets that we've been overlooking because we're focused on the wrong variables? Kīlauea is not the only place where something strange is happening. It's just the most visible, the most documented, the most accessible to anyone willing to look at publicly available monitoring data. But if you start digging into other observational domains, particularly ones that monitor Earth's interface with space, you find anomalies that don't fit standard models. Anomalies that share a common thread. They all involve timing. They all involve response to external conditions. And they all involve systems that are harder to forecast than we'd like to admit. Satellite operators have noticed something odd this year. During moderate geomagnetic storms that shouldn't cause major problems, satellites in low Earth orbit have experienced more drag than atmospheric models predicted. Drag means the satellite is encountering denser atmosphere than expected at its altitude. That shouldn't happen during routine space weather. The upper atmosphere is supposed to expand during geomagnetic storms due to heating, yes, but in predictable ways that we've modeled extensively. When the drag exceeds predictions consistently, it means the atmosphere is behaving differently than the models say it should. Either the energy input from the magnetosphere is being distributed more efficiently than we thought, or there's a secondary heating mechanism we're not accounting for, or the baseline atmospheric state has changed in ways that our reference models don't capture. Power grid anomalies tell a similar story. Grid operators monitor geomagnetically induced currents as part of space weather preparedness. During strong geomagnetic storms, these currents can cause transformer damage and widespread outages. But in 2025, grid sensors detected unexpected current spikes during storms that were rated as moderate, not severe. The currents weren't strong enough to cause major damage, but they were larger than the storm intensity should have produced. That suggests something about the coupling between the magnetosphere and the ground has changed. Maybe ground conductivity is different than assumed. Maybe the current paths are more efficient. Or maybe the storms themselves are more geo-effective than their classification indicates. Either way, the observations don't match the models. Upper atmosphere density measurements are also off. Research satellites equipped with accelerometers can measure atmospheric density directly by tracking how much drag they experience. Those measurements are then compared to empirical models like NRLM size or JB 2008 that predict density based on solar activity and geomagnetic conditions. Multiple times this year, the measured densities have been significantly higher than the models predicted, even accounting for uncertainty. The discrepancies aren't huge, maybe 10 to 20%, but they're consistent. And consistency in model error suggests systematic bias, which means we're missing something about how the thermosphere responds to energy input. Now here's where it gets interesting. Artificial intelligence systems are being used to hunt for patterns in geophysical data. Machine learning algorithms that can process enormous data sets and identify correlations that human researchers would never find manually. These systems have started flagging timing relationships between solar wind parameters and terrestrial phenomena that weren't previously documented. Relationships between solar wind dynamic pressure and seismic activity rates. Relationships between interplanetary magnetic field orientation and atmospheric lightning frequency. Relationships that shouldn't exist according to current theory, but that show up statistically significant in the data anyway. The AI doesn't know why these correlations exist. It just knows they're there. And that's both exciting and deeply frustrating, because detection is outrunning explanation. We can find patterns faster than we can understand them. We can identify correlations before we have mechanisms. And that creates a weird situation where the data is telling us something important, but we don't know what it means yet. It's like overhearing a conversation in a language you almost understand. You catch enough words to know something significant is being discussed, but not enough to grasp the full meaning. That's where we are with Earth's response to space environment conditions. We know there's a connection. We can see it in multiple independent data sets, but the physical pathways remain obscure. This is why Kīlauea matters so much. It's fast, it's visible, it's measurable in real time with multiple independent sensor types. When episode 40 erupted during a geomagnetic storm after a convergence window that included solar wind, tidal stress, and recent earthquake activity, it wasn't just another eruption. It was another data point in a pattern that's been building across multiple domains: volcanology, atmospheric physics, space weather, seismology, all of them showing signs that Earth's response to external forcing is stronger or more complex than baseline models assume. And if that's true, then every system that depends on those baseline models is potentially underestimating risk. The meta problem isn't that we don't have good models. We have excellent models for isolated phenomena: geomagnetic storms, volcanic eruptions, atmospheric dynamics. Each discipline has spent decades refining their understanding and their forecasting tools. The problem is that those models were developed under the assumption that cross-domain coupling is weak, that space weather doesn't significantly influence geological systems, that atmospheric processes are mostly independent of interplanetary conditions. And those assumptions are starting to look questionable. Not wrong necessarily, but incomplete. And incompleteness in interconnected systems can lead to catastrophic surprises. Kīlauea might be an early responder, a sensitive detector for coupling effects that other systems also experience, but more slowly or less obviously. If that's true, then watching Kīlauea isn't just about monitoring a local volcanic hazard. It's about using one of the most responsive geological systems on Earth as a diagnostic tool for understanding how our entire planet interacts with its space environment. And that brings us to the final question, the one that all of this has been building toward. The question that nobody in an official capacity wants to ask out loud, because asking it implies we might not have an answer. So what question are we actually avoiding? It's not whether Kīlauea will erupt again. It will. It's one of the most active volcanoes on Earth. Eruptions are normal, expected, well monitored. The Hawaiian Volcano Observatory does exceptional work forecasting activity and keeping people safe. That's not the issue. The real question is deeper and more uncomfortable. If Earth is more externally sensitive than our models assume, if timing correlations between space weather and geological activity are real and reproducible, then what else have we mislabeled as random? How many earthquakes that we attributed to stochastic tectonic stress release actually occurred during periods of elevated geomagnetic activity? How many volcanic eruptions that we treated as independent internal events happened shortly after solar wind velocity spikes? How many anomalies in atmospheric behavior, power grid performance, satellite operations, and ground-based sensor networks have we dismissed as noise when they were actually signals we didn't know how to interpret? If the coupling is real, and if systems can be sensitized by prior events like earthquakes or pressure changes, then our entire framework for understanding geophysical hazards might be missing a crucial dimension. Not the primary mechanism, the timing modulator, the external clock that influences when latent instabilities finally release. This is not about predicting doom. It's not about claiming the next big earthquake or volcanic supereruption is imminent because of solar activity. That would be irresponsible and scientifically unjustified. What this is about is acknowledging model uncertainty honestly, admitting that our forecasting tools might be incomplete, recognizing that planetary systems are more interconnected than disciplinary boundaries assume, and investigating those connections rigorously instead of dismissing them because they don't fit paradigms developed before we had the observational capability to see the correlations clearly. The institutional response to these ideas has been largely silence or dismissal, not because researchers are blind or incompetent. They're not. But because investigating cross-domain coupling requires funding, collaboration between disciplines that don't normally talk, and willingness to pursue research directions that might not produce clear results. It's easier to stay within established frameworks where the problems are well-defined and the methodologies are proven. It's safer professionally, but safe science doesn't always advance understanding, especially when the phenomena you're studying are at the boundaries between domains. Model lag is a real problem in Earth science. The models we use for operational forecasting were often developed decades ago based on data sets and understanding that have since expanded dramatically. Updating models is expensive. It requires revalidating against historical data. It requires computational resources. And it requires consensus that the changes are necessary, which is hard to achieve when the evidence is suggestive, but not conclusive. So the models persist, even as observations accumulate that don't quite fit, and the gap between what we can detect and what we can explain grows wider. Kīlauea's role in all of this is unique. It's not a threat in the sense of being an extinction-level hazard. It's not going to destroy civilization or cause global catastrophe. What it is an instrument panel, a real-time diagnostic for processes occurring beneath our feet and influences arriving from beyond our atmosphere. Every eruption is a data event. Every thermal anomaly is a measurement. Every correlation with space weather conditions is a clue about how the system actually works versus how we think it works. In episode 40, with its extreme thermal classification occurring during a geomagnetic storm after an earthquake that reorganized the plumbing following a convergence window with dual coronal holes and peak tidal stress, is exactly the kind of multifactorial event that should make us pause and reconsider assumptions. But let's revisit what this story is not, one final time. This is not apocalypse. There's no evidence that solar activity is going to trigger catastrophic volcanic eruptions or megaquakes that destroy continents. The correlations are about timing, not magnitude. External forcing can advance when events happen, not create events that wouldn't have happened at all. This is not prediction. We cannot look at space weather forecasts and tell you when the next eruption will occur. The internal state of the volcanic system still matters most, and that remains difficult to forecast even without considering external factors. And this is not proof. The evidence is correlational, not causal. We have timing relationships and statistical patterns, but we do not have definitive mechanisms or experimental validation. What we have is enough to justify further investigation, enough to question whether our models are complete, enough to suggest that Earth operates as a more open system than we've traditionally assumed. If Earth is more externally sensitive than we thought, then there are implications for how we assess risk. Power grids need to account for more geomagnetically induced current variability. Satellite operators need better atmospheric density models. Volcanic monitoring networks might benefit from incorporating space weather data into their warning systems, not as primary inputs, but as contextual factors that could influence timing during periods when internal conditions are already critical. It's about improving situational awareness, closing model gaps, preparing for scenarios that current frameworks don't adequately capture, and that brings us back to awareness itself. Sometimes the problem isn't the signal. Sometimes it's that we finally learned how to see it. For most of human history, we didn't know solar wind existed. We didn't know about geomagnetic storms, or coronal holes, or interplanetary magnetic field structures. Those phenomena were invisible to us, even though they were affecting Earth constantly. Now, we can see them. We can measure them in real time, and we're discovering that Earth responds to them in ways we didn't predict. That's not scary. It's fascinating. It's what science is supposed to do. Reveal connections we didn't know were there. Challenge assumptions we didn't know we were making. And force us to update our understanding based on evidence, not comfort. Kīlauea will keep erupting. The sun will keep exhaling. Earth will keep responding. And we'll keep watching, measuring, and trying to understand what the data is telling us. Episode 40 was extreme. It was well-timed. It was anomalous in specific documentable ways. But it wasn't a warning. It was a message. Earth is speaking a language we're only beginning to understand. And if we're smart, if we're humble enough to admit how much we still don't know, we'll keep listening. Because the alternative, pretending we already have all the answers, ignoring correlations because they're uncomfortable, dismissing observations that don't fit our models, that's how we miss the next big thing. Not the next disaster, the next discovery, the next leap in understanding how this planet actually works. And whether you find that unsettling or exhilarating probably says more about you than it does about the data. But either way, the clock is still ticking, and Kīlauea is still watching the sun.